Hi there! Did you know that every symmetric matrix is orthogonally diagonalisable? Well, now you do. Do you know what it means? I will tell you. First of all, a symmetric matrix is a matrix that is equal to its transpose. In the previous chapter we already met orthogonal matrices. A square matrix U is orthogonal if U transpose times U equals the identity matrix. This is equivalent to the columns of U are orthonormal. In fact, they form an orthonormal basis for R to the n. Another way to put it, U is orthogonal if and only if the inverse of U is equal to the transpose of U. Now I can explain what orthogonally diagonalisable means for a matrix A. It means that A can be written as Q times a diagonal matrix D times Q inverse for an orthogonal matrix Q. And this is the same as there exists an orthonormal basis of R to the n consisting of eigenvectors of A. Note that these eigenvectors are precisely the columns of the matrix Q. The converse of the main theorem is also true, and it is proved in two lines, as follows. If A is orthogonally diagonalisable, then A equals Q d Q inverse with Q orthogonal, so A equals Q d Q transpose. Now use the rules of the transpose operator and the simple fact that the diagonal matrix is symmetric. And you see that the transpose of A equals A, so A is indeed symmetric. Nice, no? The main theorem itself rests on three important properties of symmetric matrices. First, all eigenvalues of a symmetric matrix are real. Second, for each eigenvalue, the geometric multiplicity equals the algebraic multiplicity. And third, eigenvectors for different eigenvalues are orthogonal. Note that the first two properties already imply that symmetric matrices are diagonalisable. Namely, they imply that there are sufficiently many eigenvectors. Let's have a look at a small example first. The matrix A, shown here, is symmetric. Its characteristic polynomial equals lambda squared minus 25, and from this you can already conclude that A is diagonalisable. Namely, A has two eigenvalues, plus 5 and minus 5, which give two independent eigenvectors, and these form a basis of eigenvectors. It's not hard to compute the eigenvectors. For lambda equals 5, you have to solve a linear system, and from the reduced form you can read off that 2 minus 1 is an eigenvector. Likewise, for lambda equals minus 5, you will find that v2 equals 1, 2 is an eigenvector. About the orthogonality, compute the inner product. You see, these eigenvectors are indeed orthogonal. You can scale them to find an orthonormal basis Q1, Q2 of eigenvectors, and putting these into a matrix Q, you get an orthogonal matrix diagonalizing the matrix A. Of course, the matrix D is the diagonal matrix with the corresponding eigenvalues on the diagonal. Beautiful, isn't it? Here you see the three important properties of symmetric matrices again. The third property implies that the matrix that diagonalizes A may be taken orthogonal. Namely, for each eigenspace you can construct an orthonormal basis using the Gram-Schmidt process, and these bases put together give a basis consisting of eigenvectors for the whole R to the n. Because of the orthogonality property 3, this is automatically an orthonormal basis of R to the n. To see how it works, consider the symmetric matrix on the slide. Skipping the computations, the eigenvalues are 3, 3, 6 and minus 3. And you may, or you may not, check that the vectors v1 up to v4, as shown, give a corresponding basis of eigenvectors. Note that indeed the double eigenvalue 3 gives rise to two independent eigenvectors v1 and v2. This is precisely what property 2 guarantees. The orthogonality property states that the inner products of v1 and v3, v2 and v3, etc. should all be equal to 0, which is true, as you may check. The eigenspace for the double eigenvalue lambda equals 3 has the basis v1, v2 that is not automatically orthogonal. Using Gram-Schmidt, you get this orthogonal basis u1, u2 for this eigenspace. And replacing the first vectors by these gives an orthogonal basis of eigenvectors for the whole space. Normalizing and putting them together gives the orthogonal matrix Q that diagonalizes A. That is, A equals Q times D times Q inverse. Brilliant. For this example, again, the three properties are satisfied. Two examples is of course quite insufficient as a proof. Let's have one last look at the big three. The proof of the third property is the easiest, and I will give it here. Suppose u and v are eigenvectors for different eigenvalues lambda and mu. Then the inner product of A times u and v can be calculated in two ways. The easiest way leads to lambda times u dot v. However, using the product rule of the transpose and the symmetry of A, you see that it is also equal to mu times u dot v. Combining these two gives that u dot v equals 0, which it means that u and v are orthogonal. Beautiful again. Don't you agree? The proofs of the other two properties I leave to you. They are not so easy. But, as you might know by now, beauty is not the only property that mathematics shares with diamonds. Time's up. Goodbye.